The goal of this video is to describe circular motion using vectors in 3 dimensions. Here we have a 7-inch vinyl record. We can easily measure the radius of the entire record and the radius of the artwork sticker as 42mm and 19mm respectively. This particular record spins at a known frequency of 45 RPM, or rotations per minute. This translates to 3/4 of a rotation per second, or 0.75 Hz. Rather than describing how much of a rotation is accomplished per second, we could instead describe how many seconds it takes to complete a rotation. This is called the period, which works out to be 1 1/3 seconds. Another way of describing how fast the record is spinning would be to describe its angular frequency, which is often called angular speed. This is represented by the Greek letter omega, and is defined simply as how many radians a point on the record traverses in 1 second, which is 2 pi times the frequency f. This record would have an angular speed of 4.7 radians per second. Notice, however, that this tells me nothing about which way the disk is spinning. If I want to indicate that the record is spinning clockwise, I need to describe an angular velocity. To determine the direction the angular velocity points, use your right hand and curl your fingers in the direction of rotation, then stick your thumb out. If your fingers are curling the same way this record is spinning, your thumb should be pointing in toward your screen. Using conventional axes, we'll call this the negative k-hat direction, so our angular velocity would be negative 4.7 k-hat. If the record spins counterclockwise, our angular velocity would be positive 4.7 k-hat. In this way, by using a vector pointing perpendicular to the disk itself, I can describe which way the disk is rotating with a simple plus or minus sign. Let's put 2 pennies on the record, one on the outer edge and one on the inner edge. As the record spins, these pennies will travel in a circumference proportional to the inner or outer radius. Both pennies are at rest on the record. Therefore, both pennies complete one rotation in the same amount of time, so they both have the same angular speed. Both pennies return to their starting positions, so they both have a net zero displacement. However, the pennies have 2 different radii of rotation, so the distances they cover in one rotation are different. The outer penny actually has to travel farther than, but in the same amount of time as, the inner penny. Thus, the outer penny must actually be traveling faster. Plugging in the radii that we have, we see that indeed the outer penny is traveling more than twice as fast as the inner penny, even though they both have the same angular velocity. Let's focus on just the outer penny to make sure we know what's going on. At any given moment in the penny's rotation, it will have a velocity pointing tangent to the path that it is traveling. Because the record is neither speeding up nor slowing down, the speed of the penny must remain constant. That means the magnitude of each of these velocity vectors must be the same. However, even though the speed of the penny is constant, the velocity continuously changes since the penny is constantly changing direction. Whenever there is a change of velocity, there must be an associated acceleration. To get an idea of what this acceleration looks like, let's rewind the rotation and zoom in until the penny has barely moved at all. Now, bear in mind that the speed of the penny is constant, so the magnitude of v0 is the same as the magnitude of v1. However, in a very small time step, the angle between these 2 vectors, theta, is very, very small, which allows us to approximate the difference between v0 and v1 as a vector pointing straight down from the top of the circle, which forms, approximately, a right triangle. That is, the acceleration is perpendicular to the velocity of the penny at the top of the circle, and, by extension, everywhere along the penny's path. A change of velocity that is completely perpendicular to the current velocity serves the purpose of changing the direction of the velocity vector without changing its magnitude. Because this acceleration will always point toward the center of the circle, we call it a centripetal acceleration and denote it a sub c. Centripetal comes from the Latin words meaning center seeking. To determine the magnitude of the centripetal acceleration, let's look back at the penny over a very small distance. The penny travels along an arc, which is always of length theta r. The displacement of the penny is a straight line connecting center to center, which has both horizontal and vertical components over a small distance. Since the penny travels a distance of s can also be described as the speed of the penny times time. Notice that as theta becomes very, very small, the displacement delta x and the arc length s will be the same. This green triangle representing displacement is similar to the triangle we saw when looking at a change of velocity of the penny. In fact, the triangles are indeed similar triangles, and so the angle theta appears here. This means that our change in velocity, delta v, can be related to the speed of the penny v0, which is of constant magnitude. It is important to note that for very small angles theta, the tangent of theta is approximately equal to theta itself. So as long as we're working with differentials, we can say that delta v over the speed of the penny is equal to theta, which must also be equal to the arc length divided by the radius of the circle. Again, since theta is so small, the arc length and the displacement delta x are the same. The acceleration of the penny is then defined simply as a change in velocity over a change in time. I can solve this equation for change in velocity and plug it in for delta v here, to express the acceleration as the displacement times the speed divided by the radius and all over delta t. Delta x over delta t is the definition of speed, so the centripetal acceleration can be expressed as the linear speed v squared divided by the radius of the circle r. Plugging the values for speed and radius into this equation, I would find this penny to have an acceleration of about 0.943 meters per second. The acceleration always points radially inward. Remember that this acceleration is the change of the velocity. If the penny were to fall off the record, so this acceleration no longer exists, the penny would be left with whatever speed it just had and would continue in that motion. For the penny that was on the inner radius, because it is traveling with a slower linear speed, it'll have a smaller centripetal acceleration. To summarize, if you know the frequency and radius of an object moving in a circle, then you can describe the period of that object as 1 over f. The angular velocity of the object is 2 pi f, with the direction determined using a right-hand rule, the linear velocity of any point along the object as the distance that point covers over the period, which is equivalent to omega r, and the centripetal acceleration, which is the square of the linear velocity over r, or equivalently omega r squared.